Now I will explain the second system, personal computer authentication. Now the goals of personal computer authentication are to counter spammer botnets by authenticating personal computers by updating email clients so that every outgoing email is signed by the personal computer, as well as updating web browsers so that spammer access to free services such as webmail accounts is controlled. And the benefit of this also is that we could eliminate CAPTCHA. And these goals will be accomplished by a one-time invisible update to existing email clients and web browsers. Now, the first step in instituting personal computer authentication is having personal computers update their existing email clients and their existing web browsers. During this process, a 128-bit secret ID number will be issued to each computer. The secret ID numbers can be retroactively issued to existing computers in the following manner. Windows systems can use a hash of their Windows product ID on each computer, which is already known only to Microsoft. Apple systems, including iPads, iPhones, everything, can have the secret ID numbers generated from their unique hardware components, and any remaining systems can purchase a secret ID number via a one-time, time-consuming computation. I'll explain resistance to botnet exploitation a little later. Now, in the future, secret ID numbers can be easily distributed via network cards, as each already has a unique MAC address burned into it, so burning an additional random 128-bit number should be pretty simple. Also, a global database run by a responsible authority will be established, and this database will conceal a list of all of the world's secret ID numbers, it will conceal a single private key, and it will maintain reputation reports for each secret ID number. And this is how an updated email client will sign the outgoing email. As usual, we hash the email message, and this is where we would normally encrypt the hash with a private key. But we're not going to do that. We're going to do something a little strange. We're going to use a public key instead of a private key to encrypt this hash. And we're doing something else strange. We're throwing in the secret ID number together with this message hash. Imagine this is a 128-bit number, and we are encrypting them together. And now we have created a new type of digital signature that we will place in the email header as usual. And remember, the unique aspects of this digital signature is that the email client signs all outgoing email regardless of the sender's identity. A public key is used to sign this email instead of a private key, and the personal computer's secret ID number is encrypted into the signature. So we just send off this email. So now this email arrives, and we need to check this signature. Now the receiving mail server actually can't decrypt this signature. It doesn't have the private key. So the signature is sent to the global database, and the global database will decrypt the signature. A reputation report connected to the secret ID number is located by the global database, and the hash and the reputation report are sent back to the receiving mail server. The receiving mail server does not receive the secret ID number. So the receiver can now use the hash to verify the email and can use the reputation report to help judge if this email is spam. And when the receiving mail server is done, it will then give feedback to the global database so the global database can update its copy of the reputation report. And now I'll explain how the update for web browsers will work. And so let's say a user attempts to register a webmail account. Well, the website server will request the secret ID number of the personal computer, and up on the user's web browser, a window will pop up, and it will say, "This website is requesting verification of your computer's reputation." So the user clicks OK, and the web browser will then use the public key to encrypt the secret ID number together with a timestamp. And there it's encrypted, and the reason for this timestamp is to guarantee that this little bit of data is not reused a million times if it falls into the wrong hand, so the timestamp makes it unique. This encrypted piece of data is sent to the web server, and the web server can't do anything with it, so it sends it to the global database, and the global database sends back a reputation report, and now the web server can decide whether or not to grant this person a webmail account. Now, in terms of countering botnets, we may ask, well, how is personal computer authentication different from prior unsuccessful paper transaction schemes? And this is not a paper transaction scheme, but rather it is a paper identity scheme tied to a single global database. And also, it is easily retrofitted onto existing email and web infrastructure. Now, botnets will be stealing a vast number of these secret ID numbers from the computers they infect, but these stolen numbers are going to be rapidly deactivated and the computer owners will be alerted, so it's kind of self-defeating for the botnets. Botnets will activate new secret ID numbers by stealing computational power, but they're not going to do well with this. As an example, let's assume that activating a secret ID number solely via computation takes about 2 hours, and the zombie will send out about 10 spam before this is blacklisted. That means if you want to send 1 billion spam, you need to steal more than 22,000 years of computing time, and it would take a botnet of more than 24 million computers running 8 hours a day to send this 1 billion spam. So the goal is actually not to make it absolutely impossible for a botnet to send spam, but rather to decrease by several orders of magnitude the amount of spam it can send. So in conclusion, to summarize the anticipated effects, MTA authentication will authenticate every MTA listed in an email header. It will guarantee the message content. It will solve the problem presented by dynamic IP addresses, and it will enable SPF domain authentication despite forwarding, while personal computer authentication will authenticate the personal computer used to send every email and for accessing free web services. It will guarantee email message content, it will eliminate CAPTCHA, and it will profoundly reduce the volume of email and web spam that a botnet can produce by requiring a quote-unquote payment. With conventional existing authentication schemes, universal implementation is impossible, but with these two proposals I have today, with the cooperation of a relatively small number of software vendors, universal implementation will be inevitable. Although with these systems I'm proposing, they are meant to supplement and perform synergistically with existing authentication methods. They are not meant to replace them, so use them all. And my final argument for these systems is why not? There's very little reason not to implement them because they require very little effort by a very small number of organizations. They are invisible to almost everyone in the world, and well, if it doesn't work, then a handful of people will have wasted a small amount of effort. If it does work, then the benefit is potentially tremendous. And thank you for listening. Of course, there's still a lot of additional nuance I didn't discuss. You'll have to look at the full paper for that. But I really hope that you'll think about these issues. Thanks.